In systems engineering, it's important to understand the difference between solving a problem and building a model. When you study physics or mathematics as a early engineering undergraduate student in your first 2 or 3 years, you get the impression that the world is going to present to you problems that have to be solved. Mostly, this is an exercise in identifying the correct equation to apply to the problem, identifying the known variables in that equation, and the unknown variable, and learning to solve for the unknown. In those early courses, especially your first 2 years, there will be one solution. It will be right or wrong. And if you're lucky, you'll be able to look up the answers to the odd problems in the back of the book or something like that, so you can check your work on your homework assignment. This experience of analysis in your science and mathematics courses leads to a misconception about engineering, that there is one right answer and that all other answers are wrong. Let me explain why that's a misconception. Engineering is a design discipline. And what that means is it's a creative act. The job of the engineer is to bring forth in the real world what previously only existed in the engineer's imagination. In particular, with regard to civil engineering, it is the role of the civil engineer to conform geography to the engineer's imagination. You see a river. The river runs through a canyon. And this is the way geography exists as the engineer encounters it. But the engineer can imagine a bridge connecting two highways that otherwise might just end at the canyon. And so civil engineering is the job of conforming geography to the engineer's imagination. There is a river, but we're imagining a lake. There is an ocean, we're imagining a port. There is a desert, we're imagining a parking lot attached to an 80,000 square foot big box retail store. You can see how things have to exist in the imagination before the world can be conformed to that imagination. Well, there is no one right bridge or one right dam or one right highway. The misconception of the first couple or 3 years of engineering education is that problems present themselves with right and wrong answers, and that these can be determined objectively. That's not the way engineering works, because engineering is a design discipline. There can be an infinite number of sort of right answers. Or another way to look at it is to say all the answers are wrong. No matter what highway, no matter what dam, no matter what airport, no matter what parking lot you design, someone in this world will object to it. You drive along the highways of Arizona. I teach at Arizona State University, as you know, and it seems like everyone with a driver's license thinks they're a highway engineering expert. Well, you know what they really should have done is they should have put a ramp over here in the curve, and I can't believe what they did with this interchange. No matter what your design, somebody is going to tell you that you're wrong. Your goal as a design engineer is not to be right, because it's an unattainable goal. It applies only to those idealized problems that were presented to you in chemistry and physics and calculus and differential equations. Your goal is not to be right. Right is an unattainable goal in a design discipline like engineering. Your goal is to be less wrong. And it's kind of depressing to think of it that way. Someone somewhere is going to object to what you're doing. And because there is no right, what less wrong means is making it better. Of the whole myriad of possible designs, there may be, in some rare, ideal circumstances, one design that is better than all the rest. You might find what we call the optimal arrangement of your design variables and say, by this certain measure, by this one function by which I am going to measure the merit of my design, I have found the optimum, the best of all possible designs. Now, there are some designs that are so wrong, they're infeasible. They just won't work. The bridge won't stand. The dam won't hold. The highway kills people because it's not safe to navigate with a car. There are some designs that are so wrong, we call them infeasible, unbuildable, impractical. And then there are designs that meet all the constraints of the problem. That is, they do the job with the budget or resources that are allocated to it. They're feasible, but that doesn't make them good. It doesn't make them right. Your goal is to become less wrong in the sense that you want your design to be better. You're looking for new ideas to improve the design. There is no right. And that means there is, well, unfortunately, you'd like to say no wrong. But there is less wrong. That is your goal. And the fact is, they're still wrong. Even though there's no such thing as right in engineering design, there's certainly things you can do that are going to be wrong. Your building can fail. Your design can fail. You can go over budget. There are a myriad, an infinite number of ways to be wrong. Keep in mind your goal is to be less wrong. And to do that, you need to move from solving a problem to building a model. In a problem, you have an equation. Hopefully you've identified the correct one. You have a set of unknowns, and you learn the algebra or the calculus or the procedures required to solve for the unknown variable. The first 2 years of engineering are particularly emphasizing this approach to problem solving. But that's not the same as exploring this range of feasible design solutions. Building a model is more comprehensive than solving a problem. Every equation is a model. F equals ma is a model. And every model is wrong. F equals ma's are Newtonian approximation for how the world works. And you might say, no, that's correct. But every single physics problem that I remember from my undergraduate days says, well, assuming a friction-free plane, or assuming a friction-free engine, assuming some idealized set of circumstances, only then does F equal ma as we can observe it in our real world. Every model is wrong in some way. For example, you might parameterize F equals ma. You might say, well, everyone knows the acceleration of gravity on Earth. It's 9.806 meters per second squared. But it's not. The acceleration of gravity on Earth varies according to your location on Earth. For example, the Himalayan mountain range is so massive that the acceleration of gravity there is greater than 9.806 meters per second squared. And if you go into the middle of the Pacific Ocean, you will find that it is less. If it isn't the equation that is fundamentally wrong, then it is the way you parameterize it that is wrong. Remember, every model is wrong, but some of them are useful. When your goal is to be less wrong, you find a model that is useful. It's an approximation of the way the world works, and it represents your belief systems. It helps you think through the design that you have in your imagination as you attempt to bring that design to reality in the real world. So every model is wrong, but we build them because they're useful. An equation like F equals ma is a model. But we don't typically think of a mathematical model as being reducible to one equation. Typically, we think of several equations constituting a mathematical model. And this mathematical model is our design space in engineering. So we may have dozens or even hundreds or thousands of equations that constitute this mathematical model. And then we may have dozens or hundreds or even thousands of design variables. Our design is an exercise in choosing those variables, choosing the values that we prefer because they will realize the design we have in our imagination, choosing those values and then exploring the consequences within the mathematical model, because it is way cheaper to explore a mathematical model than it is to actually build something in the real world and explore it there. Typically then, civil engineers will start with the mathematical model and then move to the lab where you build an approximation or a prototype of whatever it is you're thinking about in the real world. It could be as simple as a concrete cylinder or a mortar cube or a steel connection or a beam. And then test that in the real world so that you could improve the model by making it less wrong, improve the parameters, tweak the equations, and make predictions about how the structure, whatever it is, might perform in the real world. In this sense, every civil engineering work is a hypothesis. We cannot model the world correctly. Every model is wrong, but some of them are useful. There are things like the waves, the wind, the earth, that we will never get right. Our goal is to be less wrong. When we do a geotechnical exploration of the subsurface conditions on a site, and we drill holes down to sample the soil conditions below grade, we can never get a perfect model of what's happening and therefore design our foundation for the specific characteristics of this site. We can only create a model, and our model will be wrong. But if we do it well, the model will be useful. That model typically consists of a set of mathematical equations and their parameters that we test either in the lab or sometimes at a prototype scale, or sometimes in the real world at a miniature scale, so that we can improve the model by making it less wrong. The model allows us to explore, in the form of a sensitivity analysis, lots of different variables, lots of different ranges of the design variables so we can see what sort of results we get. It's not possible to keep hundreds of mathematical equations in our head and intuit our way through the mathematical model that we will use to explore our design. And so we build software programs, even if it's only in Excel, although most civil engineering programs are more sophisticated than Excel. Excel is suitable for our financial analysis, for determining what the financial or economic implications of the design will be. So the difference between solving a problem and building a model. In solving a problem, you have one right answer. And that generally applies when you're starting your engineering analysis education. But to do design, you have thousands, if not an infinite number of wrong answers. And you use a model to explore those wrong answers. Your model will have a number of equations, not just one, at which you will have to choose the values of the design variables. This is your choice. And someone out there is going to disagree with you. That's okay. You must have the courage to be wrong and the motivation, the discipline to constantly test your ideas to make them less wrong. So a model is a set of equations that is indeterminate because it has more unknowns than it has equations. It's not solvable in the sense of one right answer, although there might be a set of variables that are feasible, that satisfy all of the equations. There is no one, except under rare circumstances, no one set of variables that is the best for everyone. That's the realm of operations research And we will use examples in which one best answer emerges, as long as you agree on how you're going to measure the merit of that answer, which is very rare in the civil engineering world. But we will do example problems like that. You have a project problem. If you're in my systems class, you're trying to decide whether to advise a friend to purchase a plow and go into the business of plowing driveways. To do that, you must establish the values of certain parameters in your problem. You must explore the sensitivity of your model to those parameters, and you know your model is wrong. There's no data from the future. You cannot validate your answer with data that does not exist, but you can explore your imagination. You can explore in your model the consequences of setting different values or different parameters at different levels. And you can make a recommendation, which is not a right answer. It's a gamble. It's a hypothesis on the future. You can monitor that recommendation to see whether your friend actually makes any money and whether the recommendation turns out in its outcome to be profitable. That will be the subject of my next video.